So, welcome to this next lecture. We have been looking at continuous stirred tank reactors, and just to quickly go over what we have looked at in the last lecture. Well, in a continuously stirred tank reactor, well, there is perfect back mixing. What that means is that the exit concentration is the same as the inlet concentration, and the concentration inside the reactor, concentration, temperature and all other state variables, if any, are the same at every location inside the reactor, right. So, that is meant by perfect back mixing, and because that is the case, the concentration will be the same at the exit. So, the exit concentration temperature is the same as the reactor concentration temperature, and if you write a material and energy balance around the reactor, what you will find is that the steady state conversion depends on both the inlet and the exit conditions, all right. And it is because of this that there is the possibility of multiple steady states. Note that in a plug flow reactor, given the inlet condition, you just integrate over the length of the reactor and you get the outlet condition. In a CSTR, the outlet condition depends, the reaction rate depends on the composition and the temperature inside the reactor, and therefore, the material balance has whatever is coming in and whatever is going out, and reaction rate, since it depends on the out state, you have greater nonlinearity, and because of this greater nonlinearity, there is the possibility of multiple steady states. And we, I think, discussed this. If you look at the reactor temperature and you look at the generation of heat due to reaction, it is an exothermic reaction, the generation curve is an S shaped curve. Heat transfer, let us say it is a jacketed CSTR, the jacket is at a temperature Tc, reactor is at temperature T, then the heat transferred across the walls of the jacketed reactor would be UA delta T, UAT minus Tc, and that would be a linear curve, and this linear curve may have one intersection with the S curve. So, that is the steady state, or more often than not, if the slope is lower, you will have 3 intersections, and what we saw was that the steady state over here, if I call this steady state 1, steady state 2, steady state 3, well, high temperature is steady state 3, low temperature is steady state 1, intermediate temperature is steady state 2. These two are stable and this one is unstable. We had discussed this last time, and what that means is, let us say if I am at steady state 3, I am here. If the temperature of the reactor goes up a little bit because of any reason, then because the heat removal rate goes up faster than the heat generation rate, that extra heat removal will bring the temperature back down. So, a deviating temperature is brought back. Same logic will hold true in at steady state 1. At steady state 2, on the other hand, if the temperature goes up, the heat generation rate goes up faster than the heat removal rate, therefore, the temperature will continue to increase unless you take control action to increase the heat removal rate. Okay. So, if you do nothing and the heat removal rate, the jacket temperature is held constant, then if the temperature at steady state 2 increases, it will continue to increase, and your reactor temperature will end up at steady state 3. Similarly, if the reactor temperature decreases, the temperature will continue to decrease and you will end up at steady state 1. So, steady state 2 is open loop unstable. If you do nothing, well, this temperature is bound to end up deviating to a the high temperature steady state or the low temperature steady state, all right. In practice, though, it is usually desirable to operate at steady state number 2. That is because at steady state number 3, the temperature is too high, it will kill the catalyst. At steady state 1, the temperature is too low, reaction rates are not fast enough. So, for a given conversion, the size of the reactor would be too too large, that means the reactor cost will be too high, alright. So, since you desire to operate at steady state 2 and steady state 2 is open loop unstable, this is an example where a control loop that adjusts the cooling rate so that it increases faster than the heat generation curve to bring the deviating temperature back to set point. Okay. So, control or temperature control of the reactor by adjusting the cooling duty would stabilize this open loop unstable system. So, this is an example of a control system stabilizing an open loop unstable system. You see this pen, it is open loop unstable, right. If I do nothing, it will fall, but if I if I take control action, it can be my control action was not that good, but if I if it is a longer stick, if I just keep moving so that the stick does not fall, by doing appropriate control, this pen or a longer stick can be controlled so that it does not fall, right. So, this is an example of a control system stabilizing in open loop unstable system. Okay. I think we had done till here. Now, well, stable unstable, of course. Now, heat management, you see most reactions are exothermic. So, you need to remove heat, they may be mildly exothermic or they may be highly exothermic, and here I have drawn a simple scheme where what we have is cooling water is going in the jacket and it is exiting out here. Okay. Now, if I control the temperature inside the reactor by adjusting the cooling water flow rate, let us say the temperature has gone too low, then what you need to do is you have to reduce the cooling water rate. Okay. So, what happens here is there are some inherent advantages because you are controlling the temperature of the reactor by adjusting the cooling water flow, and the cooling water flow can vary from low to high. You have not only at low flow rates there will be a significant rise in temperature of the cooling water as it moves from the inlet to the outlet. As the water moves from here to here, temperature will rise. Okay. So, the reactor will not see a constant temperature jacket. Secondly, at low flow rates the heat transfer coefficient would be low. On the other hand, at high flow rates the heat transfer coefficient would be high. Okay. So, therefore, in this configuration, in this heat removal configuration, heat transfer coefficient varies with coolant flow rate, and there is the possibility of a local hot spot because there is a temperature gradient in the jacket itself. The inlet of the jacket is cold, the exit of the jacket is hot, all right, because the coolant flow is low. Okay. So, this is, even though this is what you would think conceptually this is what should be done, this is never done in industrial practice. This is never done. Please note this down. Okay. What is done, what you will find is actually this is also not done, but the recirculation loop is what is done. Here what is done is you got cooling water going in right here, and you got a pump that is circulating the cooling water in the jacket at a high flow rate, and this flow rate is the same as this flow rate. So, the outflow or the overflow from the cooling circuit is the same as the inflow of the cold cooling water. Okay. What happens here is, you see, this flow rate, circulation rate in the loop is constant and it is very high. Since the circulation rate is high, temperature rise from here to here will be very small or negligible. So, as far as the reactor is concerned, it is seeing a jacket which is at constant temperature, all right. So, as far as the reactor is concerned, T coolant is equal to constant, and this is a consequence of the high recirculation rate. Then how do you vary the amount of heating or cooling, or the amount of cooling? So, you see the amount of heat removed, Q cool, is equal to heat transfer coefficient into area for heat transfer times temperature of the reactor minus temperature of the coolant, and the temperature I will call it temperature of the jacket, let us call it J. Tj, temperature of the jacket is constant. Okay. Temperature of the reactor minus temperature of the what? Of the jacket. Yeah. Okay. So now if you add more cold cooling water, that means if you open the cooling water valve, since more cold water is coming in, Tj will go down. Okay. So if I call this F cooling water, if F cooling water goes up, Tj goes down. If Tj goes down, Q cool, the amount of heat removed, goes up. Alright. So the amount of heat transferred across the wall of the reactor is adjusted by adjusting Tj, and Tj gets adjusted by adjusting the amount of cooling water that is being put into the loop. Okay. Now you may think that, okay, if I want to control the temperature of the reactor, what I do is I measure the reactor temperature, and if the reactor temperature is increasing, I put more cooling water. If the reactor temperature is decreasing, I put less cooling water. Well, that is one way of doing it, but there is a better way of doing it, and let us talk about. By the way, here is a comment here. You see, when you add the cooling water, the temperature of the water inside the recirculation loop will decrease. So if cooling water goes up as a step, if FCW goes up as a step, then temperature of the jacket will actually go down, not immediately but slowly. So the recirculation loop actually introduces an additional thermal lag, and because of this additional thermal lag, this control loop cannot be tuned very tight, because you change the cooling water, then the temperature of the jacket slowly goes down, and once the temperature of the jacket slowly goes down, heat transferred across the wall goes down, and then the reactor temperature responds. Okay. To speed up the response, what is done in industrial practice is that you control the jacket temperature by adjusting the cooling water flow, and if the reactor temperature is increasing, this master controller, the reactor temperature controller, which is the master controller, this is the master loop, and this one is the slave loop. Okay. So if the reactor temperature is increasing, the master loop says, well, decrease the temperature inside the jacket. The slave loop sees that the temperature set point has gone down, therefore it adjusts the cooling water or increases the cooling water to bring down the jacket temperature. Note that the slave loop can be tuned to be really tight, and if you tune it to be really tight, you will actually reduce the bandwidth, and what that will do is, as far as the master loop is concerned, it sees a faster responding jacket temperature, and since the jacket temperature is responding faster relative to what we had here, the reactor temperature controller actually sees a faster response in the well, it sees a faster well, so the thermal lag is actually reduced, because the slave loop is tuned to be really tight. Okay. So as far as the master loop is concerned, the master loop being the reactor temperature controller, it sees an overall faster response, faster open loop system, and faster open loop system means that you can have tighter tuning. Okay. So in this arrangement, temperature control would be tighter. Another advantage of this system is that if there is a, let us say, the cooling water which is coming from a cooling tower, let us say the cooling tower, there was some upset there and the water is not as cold as it should be. So if the cooling water temperature goes up, if T cooling water, if this is T cooling water, if this goes up, what will happen here is T cooling water has gone up. Because T cooling water has gone up, jacket temperature will start to go up. Jacket temperature goes up means this slave loop will say, okay, jacket temperature is going above its set point, it will increase the cooling water flow rate, and this deviating jacket temperature will be brought back. Okay. So, Tj will go up and then it will be brought back by the action of the slave loop. As far as the master loop is concerned, because the jacket temperature is held relatively constant, you will not see much of a deviation in the the reactor temperature may show some deviation and come back. So, this is, let us say, maybe I should use, well, forget about it, this is, let us say, T reactor. On the other hand, if you did the same thing, if the same thing happened here, T cooling water goes up as a step, well, then what happens? Cooling water is hotter, therefore, the jacket is hotter. Because the jacket is hotter, less than necessary heat gets removed across the walls of the reactor, therefore, reactor temperature starts to rise. As the reactor temperature rises, in response to the feedback action of this temperature controller, you will add more cooling water. As you add more cooling water, the jacket temperature goes down and then heat removed goes up, and then the deviating temperature actually comes back. So, in this case you will see that the T reactor actually shows a large excursion in temperature, a large excursion from the set point, whereas in this case you see a change in the cooling water temperature is a disturbance that is local to the slave loop. The slave loop removes it, and you will see essentially little or no impact on the reactor temperature, right. So, this is this configuration is what is most commonly applied in industry. Okay. Well, cooling water can be used if your reactor temperature is, let us say, 60, 70, 80, 90 degrees Celsius. Then you can use cooling water to remove the reaction heat. Let us say the operating temperature of your reaction of the reactor is supposed to be 200 degrees Celsius. If that is the case, what is done is you are still using water, but it's the reaction heat is used to generate steam, and that scheme is shown here. And just to describe it to you, what is done here is, this is a tank, this is a tank or a boiler tank, it has got water in it. The water is recirculated in the jacket at a high speed or at a high circulation rate or at a high recirculation rate, and because the recirculation rate is high, Tj is constant, the jacket temperature is constant. Now, reaction heat gets transferred across the walls, and this cooling water that is coming here, it gets into this flash drum, and because it is hot, see, water under pressure will be liquid, and when you bring it to low pressure, it will flash. So, in the flash tank, the hot water actually flashes to generate steam. So, the reaction heat is essentially recovered as steam to generate steam. Okay. Now, because you are losing water as steam, there is makeup water or boiler feed water that is put into this recirculation loop in order to hold the level inside the, let us just call this a small boiler, in order to hold the level inside the boiler constant. Okay. Okay, so here we have okay, what is being done here is, if the steam withdrawal rate goes up, if the steam is increasing, boiler feed water should also increase. You see, what happens in boilers is, level shows an inverse response. So, for example, if I open the steam valve, so let us say if I open the steam valve and the flow rate of the boiler feed water is constant. So, at steady state, flow rate of steam and flow rate of boiler feed water will be equal, then the level will be constant. Okay. Now, let us say steam flow rate goes up and boiler feed water remains constant. What you will find is, what happens to the level is that you are removing more steam, you would expect that the level should go down, right, but what actually happens is, the level actually goes up and then down. Okay, so you get actually an inverse response. Why do you get this inverse response? Is because if you would have seen milk boiling, you see, when you are removing more steam, when you have opened this valve, more steam is being removed. That means those bubbles get generated inside the liquid volume, and because more bubbles are getting generated inside the liquid volume, the liquid interface, the vapor liquid interface, because of the entrapped bubble, actually goes up. That is like milk boiling. Okay. Of course, it goes up, but then you are removing more steam than you are putting in water. Therefore, after some time you will, that level will keep on going down. But that initial transient will be there, where if you start removing more steam or if you open the steam valve, the level actually initially will go up, and then after some time it will start to go down. So, this is called that inverse response. And in order to, now let us say if I did my level control without having this ratio station that is shown here, if I had just simply drawn, for example, a level controller that adjusts the boiler feed water and none of the complexity that's shown here, what would happen? Boiler feed water is going, level is going up. If level is going up, it would reduce the boiler feed water. Well, the steam has gone up, you should actually be increasing the boiler feed water. Because of this inverse response, what you will have is that the boiler feed water will also go in the wrong direction. So, to avoid this or to mitigate this effect, what is done is, you keep the boiler feed water in ratio with the amount of steam being drawn out. Okay. So, this is that ratio station. So, what you have is the flow of steam, which is this guy, this is the flow of steam. The flow of steam is multiplied by a set point, a ratio set point, and that sets the flow set point for the boiler feed water. Okay. So, the steam flow or the boiler feed water is maintained in ratio with the steam flow. The ratio set point is adjusted by the level controller. So, if over long time you find that the level is actually reducing, then what you will do is you will increase this ratio set point, right. So, this arrangement essentially makes sure that inverse response in the boiler level actually does not cause the boiler feed water to go in the wrong direction. Wrong way behavior in the level does not create a deficit or too much of boiler feed water. Okay. And of course, the pressure inside the boiler is controlled by the amount of steam that is being drawn out by this steam valve. And if you want to increase or decrease the amount of heat removed across the valves, across the reactor wall, then what you do is you adjust the set point of the pressure in the boiler. That is what this temperature controller is doing. It is adjusting the set point of the pressure in the boiler. Notice that if the pressure set point is decreased, well, at a lower pressure water will boil at a lower temperature. So, the temperature, so if P is increased, boiler pressure is increased, temperature inside the jacket will go down. Okay. If Tj goes down, then UA, well, then Q cool will actually, if the jacket is colder, amount of cooling will go up, right, and vice versa. Okay. So, if the reactor temperature is increasing, you need to increase the cooling, this temperature controller will reduce the pressure set point. Okay. So, I hope this is clear. Yeah. So, here is the comment here, steam drum level will exhibit inverse response, that is what I have shown you here. And this inverse response, well, the inverse response does not get eliminated, please do not misunderstand. The boiler feed water going in the wrong direction because of this inverse response in the level is eliminated or mitigated by ratioing the boiler feed water feed to the steam flow. Okay. That is what inverse response is, an inherent characteristic of the boiler, that will be there no matter what you do. All you are doing by doing this ratioing is not confusing the direction of boiler feed water response. Okay. All right. Use of an external heat exchanger. Sometimes, let us say the reactor temperature is, I do not know, 450 degrees Celsius. So, this reactor is supposed to be operated at a pretty high temperature, 500 degrees Celsius. And you see, because 400 or 450 degrees Celsius is beyond the critical temperature of water, phase change cannot occur now. Water at 450 degrees Celsius is a gas, it will not undergo condensation because it is beyond the critical point, right. So, that being the case, operating temperature of the reactor is so high that water cannot be used to remove the reaction heat and generate steam, all right. In that case, what you do is you will use one of these oils. For example, you use cooking oil in your cooking in the kitchen. Well, cooking oil is non-volatile, no matter what the temperature, it will not vaporize, right. So, something like that. So, those kinds of cooking oils, or Dowtherm, there are some proprietary oils that are sold by companies, heat transfer oils, special oils, and then what you do is actually have that oil circulate around. You see this pump. So, the oil is circulating around like this, and this hot oil is taken to a heat exchanger, and in that heat exchanger the hot oil becomes cold and loses its heat to cooling water. Okay. So, if the reactor temperature is, let us say, 500 degrees Celsius, that is the temperature here, you will have a jacket temperature that may be, for example, 470 degrees Celsius or maybe 470 degrees Celsius. Okay. So, now the heat, the hot oil, the heat that is gained by the hot oil in the jacket is lost inside this heat exchanger. Okay. And what I have here is a bypass to this heat exchanger. So, let us say 90% of the hot oil is going through this heat exchanger, 10% is getting bypassed. Okay. Let us just say, what that means is the master temperature controller or the reactor temperature controller is adjusting the set point for the temperature of the hot oil in the jacket. Okay. So, it is and this slave loop, which is the jacket temperature controller, which is this guy, this slave loop, it adjusts the amount of bypassing. Okay. So, let us say reactor temperature T reactor is increasing. If T reactor is increasing, I would like Tj to go down, so that more heat gets removed across the walls. For Tj to go down, you see this is hot, this is cold. So, the hot and the cold streams mix and they give you the Tj that you have here. So, if you want Tj to go down, you would like the amount of hot stream being sent here to reduce and the amount of cold stream to actually increase. So, to do that, what you do is reduce hot bypass. Okay. Notice that the dynamics of this temperature, slave temperature controller, the jacket temperature controller is going to be very fast. It is like mixing hot and cold water when you take a shower. Hot water coming from the geyser, cold water coming from the overhead tank. Well, if the temperature is too hot, either you reduce the hot water coming from the geyser or you increase the cold water coming from the tank, right. So, that is what is being done here, and the moment you adjust those valves, the temperature responds immediately. So, this slave loop is going to be very fast, right. It is almost like controlling flow. Notice that if there had been no, what should I say, if there had been no bypass, then what would have happened is this temperature controller would have had to adjust the cooling water flow rate, and then because heat is getting transferred across a heat exchanger, then what would have happened is, let us say you did not have this bypass. Okay. Then what would have happened is, to maintain the jacket temperature, you would have had to adjust the cooling water. So, then what would have happened is, reactor temperature is going up, I need to reduce the jacket temperature. In order to reduce the jacket temperature, I put more cooling water in. More cooling water as I put in, let us say the cooling water is flowing in the tubes. more cold water comes in contact with the hot tubes, those hot tubes cool down, and as those hot tubes cool down, the hot oil that is circulating on the shell side, that is in contact with those colder tubes, it cools down, and therefore Tj goes down. However, this will take a long time. That is because there is a lot of mass that those tubes have, and it takes time to heat up or cool down those tubes, alright, thermal heat capacity. So, that if this is what had to be done, what you would find is that reactor temperature control would be extremely slow, and because reactor temperatures can run away, you see, if the temperature goes up, reaction rate goes up exponentially, that means heat released by reaction goes up exponentially, and that can cause a thermal runaway. So, it is important that reactor temperature be controlled tightly. To do that, the jacket temperature must be controlled tightly. For the jacket temperature to be controlled tightly, you must have this bypass. That is what gives you faster dynamics in the jacket temperature control loop. It is almost like, it is like mixing hot and cold streams. You can get the temperature immediately that you want, right. So, therefore, this for reactor temperature control is essential. Okay. I hope I have said enough on this. Then you see, typically, because you have got a cylindrical tank, the amount of heat transfer surface area that you can get as a jacket is limited, and it may so be that for the system that you are trying to remove heat of, it you just can't remove it because there is not enough heat transfer area available. So, then what you have to do is you have to bring in design innovations or design modifications, so that the heat transfer area increases. One of the ways to do that is to use an internal cooling coil. What is an internal cooling coil? Just cold water flowing around, okay. And in this case, reactor temperature is controlled by adjusting the cooling water flow rate. Internal cooling coil will give you more heat transfer area, much, certainly much more than what you will get in a jacket, okay. Alternatively, what you can do is you take out the hot contents of the reactor, that is what you are getting out here, hot contents of the reactor, they are put through an external heat exchanger. So, this is an external heat exchanger, and what is happening in this external heat exchanger is this hot reaction mixture comes in contact with, let us say, cold tubes. The tubes have got cooling water flowing inside, and this external, because the hot material is losing heat to the cooling water, this cools down the reaction mixture. Notice that the amount of heat transfer that you can, the amount of heat transfer area that you can pack inside a shell and tube heat exchanger is much more than the amount of heat transfer area you will get in a jacket in a CSTR, in a cylindrical CSTR, alright. So, you take the hot stuff, circulate it through an external heat exchanger, and the cold stuff goes back in, okay. This external heat exchanger, like I discussed previously, if you do this type of temperature control, it is going to be extremely slow, because again the cooling water will have to cool down the tubes have a large mass and large thermal heat capacity, it takes a while for the tubes to cool down, therefore, it takes a while for the temperature of this cold reaction mixture to change, right. So, again that split ranged arrangement helps a lot. Now, you are just mixing, now a part of the hot material is split, the hot and the cold streams mix, and you get whatever is the jacket temperature, or it is not the jacket temperature, whatever is the cold temperature that you desire, okay. The working is extremely similar, or is very similar to what we just saw a couple of slides ago, okay. This bypassing of the heat exchanger, so let us say 10% goes out here, 90% goes down there. The moment you change the amount of bypass, this temperature, a very fast response to, you see, the moment this temperature changes, it is mixing with the hot reactor contents, that mixing hot material here mixing with the cold stream here, and if this is colder because I changed the bypassing, well, this hot reaction temperature will respond much faster than if I did it this way, where I am putting in more cooling water and the tubes are becoming colder and then this material is becoming colder. That will take a heck of a long time. Okay. So, this is what is done, this is not done. Okay. So, the comment here is bypassing improves dynamics. Indeed it does. All right. Okay, let us see external condenser. Now, sometimes you have got a reaction mixture which is two phase. That means, reaction is happening in the liquid phase, but the liquid phase is so hot that you got vapor also in equilibrium. Okay. So, what you do in that case is, well, this vapor is taken to a overhead condenser. In the condenser, what you have is cooling water is coming in, the vapor condenses on the cold tubes and drops down and it is put back down in. Okay. In order to hold the pressure inside the reactor constant, what is done is you essentially manipulate the amount of cooling water flowing in. So, essentially by adjusting the condensation rate, you see boiling is happening because reaction is exothermic, heat is getting generated in the reactor and that reaction heat is causing boiling. So, the vapor is now if more reaction heat is released, well, more vapor will get generated. If more vapor gets generated, you have to condense more vapor, otherwise the pressure will shoot up. All right. So, that is what this loop is doing. What this loop is doing is essentially adjusting the condensation rate to keep the pressure constant. So, what you are doing is whatever vapor gets generated because of reaction, that is getting condensed in the condenser, and to do that you are adjusting the cooling duty inside the condenser, that is by adjusting the cooling water flow rate. Okay. How do you adjust the temperature? Well, you adjust the set point of the pressure controller. And how does this work? Well, the higher the pressure, by vapor liquid equilibrium, at a higher pressure a mixture boils at a higher temperature. Okay. So, if you want a certain temperature and the temperature is increasing, what you would do is reduce the pressure set point and then temperature will get back down. Notice that in this scheme you are not controlling both the temperature and the pressure, you are controlling the temperature by adjusting the pressure set point. All right. So, like I was saying, in this case whatever is the pressure set point, this pressure set point, that is what gives, at that pressure whatever is the boiling temperature of the liquid inside the reactor, well, that is the temperature that you get. If you are not happy with that temperature and you would like a higher boiling temperature, well, then you increase the pressure set point. So, if you want T to be high, to increase, to do that you will have to increase the P. Okay. That is what this temperature controller is doing. You cannot control both the temperature and the pressure to be independent, and that is because if you try to do that, this system will never become it will just, the temperature guy will screw the temperature will affect the pressure will affect the temperature and they will never settle down. Okay. That is what is likely to happen. Okay. Why is that? Because temperature and pressure are related through vapor liquid equilibrium or the boiling. Okay. So, well, so that is something that you need to be aware of. This is something typically production for exothermic reactions. You would like to produce as much as you can, because the more you produce, we have got a volume driven process industry, the more you produce the more profit you make. Okay, because whatever you produce gets sold in the market. So, how do you make maximum profit? By producing as much as you can. Now, what happens is, because the reaction is exothermic, as I try and increase the production, increasing the production means more reaction happens, that is how more of the product will get formed. More reaction happening means more heat gets generated in the reactor. Okay. So, as you are trying to maximize production, well, your ability to remove heat will become ultimately a constraining, will be a factor that constrains the maximum achievable production. So, as you are increasing the amount of feed to the reactor, more and more heat gets removed, and then what will happen is, you will reach a state where further, input to the reactor cannot be increased any further, because you cannot remove more heat. You have reached your maximum heat removal capacity. Okay. So, well, like for plug flow reactors, we say that, okay, since I want my reactor to operate at maximum heat removal, what I do is, this is 100% open, the cooling water valve is wide open. So, cooling water as much as has to be put in is getting put in. Okay, fine. Then, in order to control my reactor temperature, what I do is, I adjust the amount of fresh feed that is going in. How does that work? Well, if the reactor temperature is increasing, that means I have put in too much reactants. I need to reduce the amount of reactants being put in. That will reduce the composition of the reactants inside the reactor, and since the composition goes down and reaction rate will typically, if the reactant concentration is more, reaction rate will be more. If the reactant concentration is less, reaction rate will be less. This is mostly typical. So, in that case, if temperature is increasing, I reduce the amount of feed, reactant concentration goes down, amount of heat generation goes down, deviating or increasing reactor temperature comes back. It is just that it is never done in practice, and the reason why it is not done in practice is because the amount of material that is stored in the CSTR is a large amount. So, let us say temperature is going up, let us say temperature has gone down. Okay. Let us say temperature is going down. Because temperature is going down, what you would do is, well, temperature is going down, that means I am removing more heat, that means I can add more feed. So, I start adding more feed. As I am adding more feed, the concentration of the unreacted material inside the reactor goes up. Okay. Of course, because of the large mass stored in the CSTR, this increase in concentration will happen slowly, it will not happen immediately, it will happen slowly. Then, because sufficient amount of material or the concentration has gone up sufficiently, what that will do is, the amount of heat released will actually start to increase, because the reaction rate is increasing. Now, because heat released increases, well, temperature starts to go up, back up. Now, as temperature starts to go up, notice that as temperature goes up, reaction rate goes up exponentially. What that will do is, actually, temperature will start to go up much faster, and this leads to the possibility of a thermal runaway. I am not saying it will happen every time, just that there is the possibility of a thermal runaway, because what is happening is, when the temperature was down, you allowed burnable material or fuel to accumulate. Then, once the temperature starts to rise, this unreacted fuel that is there sitting inside the reactor, it can catch fire, so to speak. And what I mean by catch fire is, the reaction temperature will then just shoot off and you can have a runaway. So, this scheme is susceptible to thermal runaway. Okay. Therefore, it is not recommended. It may be used for reactions that are only mildly exothermic. However, such reactions are very rare. Maybe you will get such reactions in the pharmaceutical industry, maybe biological, fermenters and so on and so forth. Certainly not in the process industry, certainly not in refineries and petrochemical industry. Okay. Mildly exothermic reactions in petrochemical or refining processes are very rare. Let's just put it at, let's just say that and leave it at that. Okay. So, what is done is you apply valve positioning control. How do you do it? Well, you got that standard thing. Well, what is that standard thing? Well, even though I have shown it as flow controlling cooling water, what actually is going on is, you know, there is a recirculation loop. This is overflow, and there is a large circulation rate. So, what you are doing is the jacket temperature is controlled by the amount of cooling water that you are putting in, okay, and the jacket temperature set point is coming from the reactor temperature. This is how conventional control is done. Now, because you would like that for maximum production the cooling water valve be nearly fully open, what you do is you take this cooling water valve position, send it to a valve positioning controller, and this valve positioning controller then adjusts the feed to the reactor. Notice that, let us say this cooling water valve is only 50% open. Then what the valve positioning controller will see is, okay, cooling water is only 50% open, it should be 90% open. It will increase the set point of, it will slowly increase the set point of the fresh feed to the reactor. As the fresh feed to the reactor goes up, because reactant accumulates inside the reactor and the reactant composition goes up, reactor temperature will start to go up because reaction rate has gone up. So, more heat is getting released. As reaction temperature goes up, the reactor temperature controller reduces the temperature of the jacket. The jacket temperature controller then increases the amount of cooling water that is being fed in. What that means is this cooling water valve becomes open. So, 50% will slowly become 60%, 70%, 80% until you reach 90%. You do not hold this at 100% because 10% or maybe 20% margin you want to keep. And why do you want to keep that margin? So that should the temperature increase when this valve is 90% open, I still have that 10% margin to bring that deviating temperature back to set point. Okay, maybe for a reactor this should be probably 80%. All right. So, this is how this is how it is ensured that you are processing as much feed as you can without compromising on tight reactor temperature control. You see, in the previous case the temperature control had to be loose because of the large lag associated with the large amount of material accumulated inside the reactor. In this case, temperature control is through heat removal through the jacket, and that is fast. Okay. So, this is valve positioning control for maximizing throughput through the reactor, maximizing the feed processed by the reactor. Okay. Why is it relevant? Well, you want to maximize production, that is why, and in the effort to maximize production, your heat removal in the CSTR actually limits your production. Next we will cover heat exchangers. I think I will stop today's lecture here and we will take heat exchangers next time. Thank you.